Hi everybody, Physics Ninja here. Welcome to my video today on the 2D tetherball problem. Tetherball is kind of a fun game. You have a ball, you hit it, and you try to make it wrap around a post before the opponent can hit the ball. In this case, what we're going to do is consider a 2D tetherball. So we're going to take gravity and that z-axis out of the problem here, but we're still going to have a mass that's attached to a string and that's connected to a post, and it will simply wrap around the post. In two-dimensional, this is kind of what it looks like. Now this problem here came up because I've been looking at this other problem called the coffee mug and the string problem. And in that case, what I do is, I did a short on this about a month ago, is you release a small mass and it's connected to a string to a coffee mug. And so the coffee mug is going to start to fall, and then that small mass is going to wrap around a post. And as it starts wrapping around, you'll see that it starts spinning faster and faster. So this is kind of what motivated. I'm not quite done solving the coffee mug problem yet, but this other problem came up as I was thinking about it, how to include the diameter of the post and friction and so forth. So for today, what we're going to do is we're going to focus on this 2D tetherball problem, simply a mass connected to a post by a string of fixed length L. That's it. You give it an initial angular velocity and it will start to wrap around the post. How long does it take before it hits the post? That's the simple question. I'm going to do this using two approaches. We're going to use Newton's laws of motion to set up sums of the forces, sums of the torque, in order to obtain an equation of motion. I'm also going to, in the second part, we'll use Euler-Lagrange method in order to obtain the same equation of motion that you would with Newton's laws. I'm going to solve them after using an analytical method, and also solve the equations using a numerical method. Put a little bit of Python code together to get the solution, to get the position of this mass as a function of time. At the end, I'll share with you just some small animations that I've created in order just to just see the simulation, see how the mass and different physical quantities, how they change as a function of time when this mass wraps around the post. All right, that's a rather long introduction. Like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It's the best way to support what I do. All right, let's get started. Okay, so here's the first method that we're going to use. We're simply going to apply Newton's second law to this problem. So we're starting out here. The length of the string that I'm considering here is simply a length L. And I am also going to be giving this mass here some initial angular velocity, which I'm calling omega 0. Okay, so that's the angular velocity at time 0. Now, as it starts to move down in this direction, I'm going to define this direction as being a positive theta direction. Okay, so this is just my choice. Okay, the rope will start to wrap around this cylinder over here. And the amount of rope that's wrapped around the cylinder depends on the radius of the cylinder, which I've denoted as A, and depends on that angle theta. So this amount of arc length here is simply A multiplied by theta. So that means that the rope is getting smaller, okay? The length of the rope, whatever is left here, is going to be, well, that's L, what I started out with, and how much rope is being wrapped around, okay? That is basically what R prime is, right? What is the radius of the point of contact to the mass over here? Now, there's only one force acting on the system once I let it go. It's simply the tension, and then the mass is going to simply start wrapping around that cylinder. So the starting point here for us is, well, let's define some coordinate systems here. I've got the standard XY coordinate system, which is defined here with respect to the center of that cylinder. And I've defined some other unit vectors here, and I could have drawn them down over here, I suppose. Maybe that would have been clearer. I could define ER right here, and then E theta is going outward like this, E theta. Okay, so ER will point from the origin all the way to going radially out from that point, and E theta is perpendicular to that. All right, so imagine here I wanted to describe right at this position what is the position of that mass. Okay, so clearly here, if I've defined these unit vectors ER and E theta, it has to have both components. All right, so this is how you would write the position vector for this mass at this instant in time. So first of all, it's going to have an E theta component. All right, and the magnitude here, again, it's going along this direction here, so that is, the magnitude is A in that direction. And then I need to know what this component is. Well, that component here, what I'm left with is basically that R prime value. That is L minus A theta, and then that's multiplied by that unit vector ER. Okay, so that's it. That is the position vector written in terms of cylindrical coordinates that I've defined here in this figure. All right, so what is next? The next thing we want to do is we want to determine what is the velocity of that particle at this instant in time. So all you have to do here is you have to evaluate what is the rate of change of the position. That's it. Okay, now this is a little bit tricky because these vectors here, these unit vectors, are also changing directions as this wraps around. So when you evaluate this derivative, you have to take the derivative of both of those terms. Let's go ahead and see what that would look like. So I would simply write, well, let's do the derivative of the first term. A is the radius of that cylinder, so that is a constant. And now I'm left with this. How does this unit vector here change with respect to time? All right, the next term now, here I have two terms. All right, I've got this angle theta that's changing with respect to time, and I've also got the unit vector. So you've got to apply the multiplication rule here to find the full derivative of that with respect to time. So let's go ahead and do it. So the first term, you differentiate the first term with respect to time. You get minus a, what else? Theta, the derivative of theta with respect to time, multiplied by ER. And then what? Plus, now you keep the first bracket the same, and you differentiate the second term with respect to time. DER with respect to time. All right, so now what we are left to do here is we have to evaluate this term and this term. Okay, and in order to do that, what we're going to do is write down the unit vectors in terms of I and j vectors, unit vectors, and then we're going to differentiate them with respect to time and see what that gives. All right, so we start by writing down these unit vectors. So maybe let's start with the vector ER. So how would I write ER? Let me go ahead and write it here. The angle theta here is defined here with respect to the y-axis. It also, you can put inside this small triangle over here. And that's kind of easier to help you write what ER is here in terms of I and j components. Again, I've defined the positive angle theta to be going here in the clockwise direction. This might be different than what's typically done, but again, it's kind of my choice. I decide which coordinate system I want to use. All right, so this is how ER would be written as. It would be written as cosine of theta multiplied by I hat, and then minus sine of theta multiplied by j hat. And I can also write E theta. Okay, E theta then, again, for that one, I think it's kind of helpful. Oh, here, it's best to use this case over here. You can see exactly what's going to happen. Here I'm going to get sine of theta I hat. And what else? I am then going to get plus cosine of theta j hat. All right, we're not interested in those vectors. Again, I'm interested in how those vectors change with respect to time. And I need both derivatives of these vectors. So let's start with the ER. So I would do DER dt. Again, the angle theta changes with respect to time. The I and j unit vectors do not change with respect to time. So this term here becomes this. It becomes minus sine of theta multiplied by the derivative of theta with respect to time. I'm denoting that by theta dot. So let me just define this up here. That is d theta dt. All right, and that is the I hat component. And what else? Now minus cosine of theta, theta dot, j hat. Well, now you can see right away that other than this negative sign, this looks kind of similar to that E theta. So you got to factor out, say, the negative sign. You could factor out this derivative of the angle theta with respect to time, and now you're left with that unit vector E theta. So that's going to be useful for us. Next term we want is, how does the unit vector E theta change with respect to time? So again, you take the derivative of this, that's cosine of theta, theta dot I hat, and then what? Plus sine of theta, theta dot j hat. All right, now again, if you look at the form of that vector, factor out the constant terms, or the terms that are in all, that multiply both. You can see it's theta dot over here. So here we're going to be left with dE theta dt is simply theta dot multiplied by the vector, the unit vector ER. Okay, so now we're going to go back to the velocity expression, and let's get rid of those derivative terms and simplify it just by introducing just these terms over here. All right, so what do we have? We have A, dE theta dt. dE theta dt is simply theta dot multiplied by the unit vector ER. All right. The second term, I'm not going to touch it because it's already written in terms of the unit vector ER. And you can see that it's exactly the same with an opposite sign. So that is going to cancel. And then we're going to be left with this term, L minus A theta. And now DER d theta is the first derivative I evaluated. That is minus theta dot E theta. All right, let's go ahead and simplify. This term leaves, and at the end, look at what I can write. My velocity of that mass at any instant in time, you can write as minus L minus A theta. That is simply that length of the rope that is remaining, multiplied by theta dot. What is the angular frequency at that time? And the direction, well, sure, the direction, just look at the vector. The vector here is in this direction. That is in the minus E theta direction, the way you have it defined. So that is the expression for the velocity of the particle that we have as a function of time. All right, the next thing I want to calculate is what is the angular momentum about this origin? Now remember the definition of angular momentum. All right, now one thing to be careful is that I'm going to use the same letter L here, but L is a vector, and this is the angular momentum vector. This is defined as R cross P. P is the linear momentum, which is simply the mass times the velocity. All right, now we've defined both of those vectors, right, previously. So let's just go ahead and write them out. So we have A E theta plus L minus A theta. Now this L is the length of the string, so be a little bit careful with that. And that is in the ER direction. And then we have to take a cross product with the mass times the velocity. The velocity is what we have up here. That's minus L minus A theta, theta dot, and that's in the E theta direction. All right. Now, the cross product between E theta and this E theta will give you 0. The only thing we're really left to evaluate is we need to know the cross product between the unit vector ER and E theta. Well, guess what? That is a unit vector in the Z direction. Just call that in the K hat direction. So our angular momentum is going to be actually in the negative K hat direction. And we'll come back to that point in just a second. Well, let's just evaluate this. So you should have minus M, take that term to the front. We should have two of these terms. That is really the moment of inertia, right? The instantaneous moment of inertia of that term, and then multiplied by the instantaneous angular velocity of that term, and everything here is in the K hat direction. That's the angular momentum at any point in time as this mass wraps around the post. All right, next thing we want to do now is if you're going to apply Newton's second law for rotation, for example, we have to calculate the torque about the same point. So let's go ahead and do that. All right, my goal now is to calculate the torque about the same origin here that I've considered for all the other vectors. So if you apply the definition of the torque, it's R cross the force. And my force is the tension, which is always acting in the direction of that rope. All right, now if you evaluate this cross product here, what you're going to get is it's going to be A, right, the distance, that's kind of our moment arm over here, multiplied by the force. A is the perpendicular distance from that line of action of the force to the pivot point. So this is kind of a quick way of calculating the torque. Notice the direction of the torque, okay? R cross T gives me a vector that's in the positive Z direction. Now, if you apply Newton's second law to this problem, think about Newton's second law for rotation can be written as something like this. If there is a torque about any point, there is a change of angular momentum about that same point. So what we have here is we do have a torque, yes, which means that the angular momentum about this origin right here is not a conserved quantity. It means it's going to change the angular momentum with respect to time. So we're not going to find that L is constant if I've described L with respect to this origin right here. Okay, so now I'm applying Newton's second law of rotation to this problem. The torque I calculated. The torque was simply A times the tension. That was in the Z direction. The angular momentum I also calculated, right? The angular momentum was given by this expression over here. But for Newton's second law, what I have to do now is I have to differentiate this with respect to time. So there's going to be a lot of terms here, right? There's going to be, when I differentiate it, I have to worry about that term, and then I also have to worry about that term right here. So I do have to differentiate both of those with respect to time. All right, so take your time when you do this. This is what I got, okay? So the first term right here is taking the derivative of this first term. There's a 2 that comes out in front, and then you have to take the derivative of the inside of the bracket. That gives us another theta dot, so that's why you get the theta dot squared. And then at the end, you also have to take the derivative of the inside. That's another factor of minus a that comes out. The second term is easier because now you just leave the first term as is, and then you simply differentiate the theta dot with respect to time. That gives us the second derivative of the angle theta. So that's actually the angular acceleration right here. And that must be equal to the torque. Again, everything here is in the z direction, so I've just taken those components out, right? This is all we're looking at are the z components. There's no other direction for angular momentum and torque in this problem. All right, so what do we have to do now is my goal is to simply, let's get an expression for the angular acceleration, this theta double dot right here. All right, just clean it up a little bit. I got rid of, oh boy, I think I made a mistake here. Oh no, okay, just be careful when you take care of all of these negative signs here so that there's 2 negative signs, so the first term becomes positive, and now the second term will remain negative. All right, now my goal is simply to isolate what this angular acceleration is, bring that term over to the other side and divide through by this whole term, and you should have this expression right here for the angular acceleration. Now, this is still written in terms of the tension force, right? So it's not the most practical form right now because the tension force itself will depend on the angle and how fast it's spinning. So what we're going to do is we're going to first try to eliminate what is this tension force here in the second expression. And for that, all you have to do is look at the radial expression. Look at Newton's second law and apply the forces here in that radial direction. So let's go ahead and do that. Okay, the next thing I need now is I need to get rid of that tension force. The way I'm going to do that is I'm going to apply Newton's second law. And for me to find Newton's second law, I need to know what the acceleration is, right? So the acceleration then is simply what is the derivative of this velocity vector here with respect to time. I'll be a little bit careful when you do this. There's actually 3 terms that change with time. There is the angle theta, there is the angular frequency, and there's this unit vector here. So let's be a little bit careful when we evaluate this term. All right, so what I do is I first evaluate that first term. So if I differentiate this bracket over here, I'm going to get minus, what else? Theta dot, e theta, that'll just be staying the same. And now here I'm left with minus a theta dot. Okay. Next thing I want to do is I want to differentiate the middle term here. Well, that one's easy, so that everything else stays the same. Here I'm left with theta dot dot, and this is still along the e theta hat direction. And then the last term now is I want to differentiate that unit vector, so that means all the other terms stay the same. And I'm going to get something like this, L minus a theta, theta dot, and this becomes squared, and then I change that unit vector. So that's taking the derivative of e theta with respect to time. So let's go ahead and kind of group some of these terms together. This is what you get. You get a theta dot squared minus L minus a theta, theta double dot, second derivative of theta with respect to time. All of that is, so those are 2 terms in that theta direction. And then we have minus L minus a theta, theta dot squared, and ER. So that is our acceleration in this theta direction, and this here is the acceleration here in the radial direction, the way we have it here. Okay, so now we go ahead and think about how would you apply Newton's second law. Well, look at this force here. This force is the force of tension. It's the only force acting on this system right here. And that force, guess what? The force, if you write it as a vector here, it only has a radial component over here. I would write it as minus t multiplied by ER. That's it, that's all. So guess what? That means that if you apply Newton's second law, that has to be equal to the mass times the acceleration in that radial direction. Okay, and this is the amplitude, right? That's the amplitude AR that we have over here. So this automatically gives me an expression for that angle, for that force T. So T at the end of the day, you could simply write as M and L minus a theta, theta dot squared. So this is going to be an important expression. We're going to go back into my torque expression, get rid of the tension using this. The other term that's kind of interesting is this one, right? A theta. A theta is the acceleration along that theta direction. Well, guess what? There is no force along that direction. So this term must be equal to 0. So this automatically gives you an equation of motion for this problem because you have to solve this expression. We have a theta dot squared minus L minus a theta, theta double dot equals to 0. Go ahead and get an expression here for my theta double dot for the angular acceleration of this problem. Bring that term to the other side. You get minus a theta dot squared, and here you get L minus a theta. That is an equation of motion. Actually, what I ended up doing, I'm sorry, I have the wrong sign here. Let's go ahead and get rid of that. When I bring that on the other side, it becomes negative, and I have another negative over here. I apologize for that. All right, so here's an equation of motion that we're going to try to solve. Relates the acceleration, the angular acceleration. It's related to the angular velocity and also to the angle theta. So this is an important equation. Now let's go back into the torque equation and substitute this tension and see what you get. All right, so all we're left with now is, let's go back to that previous slide. So what do we have here? We had just eliminate tension over here. So instead of having tension in this expression, what I'm going to do now is I had an expression for tension. Let me go ahead and just give myself a little bit more space. So I'll have the A here that's left over. And the tension force, which we just solved for, was M. Now careful, this is L minus a theta. And it was only to the first power. And then we also had a theta dot squared term. So I'm going to have to include a theta dot squared term. Theta dot squared term. All right, now we got to do a little bit of algebra, and look what happens, right? The masses cancel out, one of these cancel out, and look what you're left with, 2 minus 1 of the exact same term. Now this might not jump out at you right away, but to me it does. It's A multiplied by theta dot squared divided by L minus a theta. This is the exact same equation of motion that we just got, right? And we got that equation of motion by applying Newton's second law and realizing there was no acceleration here in this theta hat direction. So it's nice whether you use the torque equation or you use Newton's second law for linear motion, just applied to this coordinate system here, you're going to get to the same equation of motion. And this is it. This is our place to start now. And we simply have to solve this. And we're going to solve this 2 ways. You could solve this analytically, just using a couple tricks for integration, or we could solve it numerically. So I'm going to do both, show you how that's done. All right, we're now going to use the Euler-Lagrange method in order to get to the equation of motion. For this, I'm going to just kind of start where I already did. I already had an expression for the velocity, and I had an expression for that unit vector here in terms of I and j components. So what I could do right away here is I could write v, my vector. Let's just write it in terms of I and j components. So what would that give? I'd get minus L minus a theta, the angular frequency. And now here I'm going to have an x component that is sine of theta, and that is along I. And now I'm going to have a j hat component. Now let me give myself a little bit more space here. Let's lower this. See. Okay. Now, if you substitute again the unit vector here, you're going to have a j hat component, which looks similar, except now I'm going to have this cosine of theta. All right. The Lagrangian, remember, is defined as the kinetic energy minus the potential energy. But in this case, our potential energy is simply 0 because everything is simply on the surface here. There's no friction. This is all you have is only kinetic energy. And the kinetic energy you simply write as 1/2 mass. And here I would write it in terms of what is the velocity in the x direction squared plus what is the velocity in the y direction squared. All right, and well, these are the components, right? These are the components, Vx, which I'm calling x dot. And here is the component in the y direction. This is what I call Vy, and that is y dot, the derivative of y with respect to time. Let's fix that. All right, so all you have to do now is substitute in here, square both of those components, and once you square it, look what's going to happen. You're going to get a sine squared term over here, and you're going to get a cosine squared term over here, and everything else is going to be the same factor in the front. So that you use the identity, and at the end you can easily show that the Lagrangian for here is 1/2 m, and now it becomes this, L minus the length. Okay, now I have another L. Oh my goodness. This problem can get really complicated if you don't keep track of everything. Theta dot. So let's just remember what this is. This is the Lagrangian. This here is the initial length of the rope. Maybe I should have called it L naught. Length of rope. Okay, and I think that is fine. Now one thing, so I can't forget to square that term. Okay, so that is the Lagrange. Now I'm going to do is I'm going to form the equations of motion here by differentiating this with respect to theta and with respect to theta prime. So let's go on the next page and obtain our equation of motion using the Euler-Lagrange method. All right, so here's the Lagrangian and here's the Euler-Lagrange equation. So all I have to do is now evaluate all these partial derivatives and substitute into my Euler-Lagrange equation. It'll give me my equation of motion. So let's go ahead and start this. We find the derivative of the Lagrangian with respect to the angle theta. Okay, with respect to the angle theta, it's only this first term that appears here. What I'm going to get is m L minus a theta. All right, and that other term remains a constant. And now I have to differentiate with what's inside that parentheses. I get a minus a that comes out over here. All right, the next term now is take the derivative of that Lagrangian with respect to theta dot. Theta dot only appears in that second term over here. So again, that 2 cancels out. You're left with L minus a theta. Now this term is squared, and here I'm left with theta dot. Now the next thing we have to do is you need to evaluate the time derivative of this entire term. All right, now this is a little bit more complicated because there are 2 terms here that depend on time. So there's the first term that depends on time. If I differentiate that with respect to time, I get 2m L minus a theta. Okay, what else? Now I have to differentiate what is inside that parentheses. So I get minus a and d theta dt. But there's another theta dt over here. So this becomes theta dot squared. All right, that's the first term. And now, well, I have to use that chain rule. Now I have to differentiate the second term with respect to time while leaving that first term constant, a theta squared. And this becomes the second derivative. All right, so we've got both terms. All we do now is go back and substitute. Well, the left-hand side is over here. The right-hand side is over here. Put everything in that Euler-Lagrange equation, and we're going to have our equation of motion. So 2m L minus a theta. Let me bring that a term to the front just to clean things up a little bit. So there should be minus 2ma right here. And this is a theta dot squared term. The next term is m L minus a theta squared. And now the second derivative with respect to time. And that there must be equal to, again, there's a minus sign here, minus ma L minus a theta and a theta dot squared. So now we have to simplify things. Well, you can see I can get rid of one of those. That appears in all the terms, so you can divide through as long as it's not equal to 0. We should be fine. The other thing are the m terms leave. A doesn't appear everywhere on that term, so you do have to be a little bit careful here. Now the only thing I have to do is I want to isolate for this here, the theta double dot. So I bring this onto the other side. It's the exact same, but it'll become positive, but there's a 2 here at the front. So that means that this side here is going to be left with a, and I'm only left with theta dot squared. Over here, what I have to do at the end is I have to divide through this entire thing by L minus a theta. And that is the second derivative of theta with respect to time. And this is really what I am trying to solve for now, right? This is my equation of motion. And guess what? It's the same equation of motion that we obtain using Newton's second law. This is just an alternative approach. Equation of motion. Let me spell that correctly. Now, our initial conditions for us in my setup, I have that the initial angle here at time 0 was, say, 0 radians. But I do give it some initial angular velocity. So this, we're going to have to give it some value. So I can call it theta dot 0 at time 0. All right, so based on these two initial conditions, you want to solve this equation. Let me show you how to do it analytically first, and then I'll show you a little Python program that I built in order to solve this differential equation. All right, so I'm going to show you a little trick in order to solve this differential equation right here. I didn't remember this trick. I kind of had to go back and look at things in a little bit more detail. But this here is the trick. So what you first do here is I bring the theta dot squared term over on this side. So here I'm left with simply a and L minus a theta. All right, the next thing I'm going to do is I'm simply going to multiply by one theta dot. So if I do that, one of them is going to cancel over here. So I'm going to be left with theta dot dot divided by theta dot equals to a L minus a theta, and then I do have a theta dot over here. Now, let's remember how things are defined. So omega is what I'm really calling theta dot, and that is really the derivative of that angle with respect to theta. This theta double dot is then the derivative of omega with respect to time. All right, so let's go ahead and think about substituting things into here. So I have 1 divided by omega, right? That's the angular frequency term. This is the second derivative term. But in terms of omega, it's d omega dt. All right, now what do we have? We have a L minus a theta. And what is theta dot? Theta dot is really nothing more than d theta dt. All right, notice we have dt's on each side. So this is what I mean by it being separable. We only have omega terms here on the left-hand side, and we only have theta terms here on the other side. So all we want to do now is you simply want to integrate here, and we're going to integrate from some initial angular velocity all the way to some final. And on this side, we're going to integrate from some initial angle all the way to some final angle. All right, so this is a pretty straightforward integral to do. I'm going to let you figure that one out for yourself. You could just do a substitution for u, for example. You can set u equals to L minus a theta, and that is a straightforward integration that you should be able to do. The result at the end of the day is you end up getting natural log here of omega divided by omega 0. And on this side, you're going to get the natural log. Now, you do got to be a little bit careful with these limits. That's the initial angle. And for us, this term is 0 here, the a theta 0, just the way I've set up that system. And boom, that's it. All right, my goal at the end was always to obtain a, now I'm not quite done, right? My goal is to obtain what is the angle theta as a function of time, right? Can I get an explicit one? An explicit equation that tells me exactly where I'm positioned as a function of time. Right now I have something that links the angle theta to its angular speed. But it's still going to be useful to us. What we're going to have to do again is going to integrate this expression. Now again, here you can cancel out the natural log terms since we have them on both sides. So let's just go ahead and just write this. This is going to be our starting point for the next part of the calculation. So here you have L minus a theta 0. And here I have L minus a theta at some time t. Let's call it theta. All right, so, and remember what omega is. The definition of omega is d theta dt. All right, so is there a way to solve this, another differential equation? And there is another way to do that. So let's go on the next page and finish off this problem and get one expression for theta as a function of time. All right, so to solve this differential equation here, I'm going to first simplify it by using my initial condition that initial angle is 0 for my problem. Now bring all the theta terms to one side. You get L minus a theta d theta. And then on the other side, you're left with this, omega 0. That's that initial angular velocity, that initial length of the rope, and dt on this side. All right, this is a pretty straightforward integral. Again, I'm integrating from 0 all the way to some final angle. And here I'm integrating from time equals to 0 to some final time. So let's go ahead and do this. So this is what we get. We're going to get L, this is theta final, minus a theta final squared divided by 2. And this here term becomes omega 0 L multiplied by t. So what we have here is a quadratic equation. Bring all the terms over onto the right-hand side. So you have 0 equals a over 2 theta final squared minus L theta final, and then plus omega 0 L multiplied by t. This is a quadratic equation, and all we need to do is solve this quadratic equation to get theta as a function of time. All right, so for that we can write right away. It's minus b becomes L. Now, plus or minus the square root of b squared, that's L squared, minus 4ac, minus 4. I'm going to be left with 2a for that term, and then the c part becomes omega 0 times L. And then all of this here I have to divide by 2a, and that simply becomes a because the 2 cancels out with the factor of 1/2 here. All right, now the physical solution for us, remember, we have to satisfy that initial condition right here. Okay, the initial condition requires that when time is 0, that angle better be 0. Okay, so when time is 0, what I have to do then is I have to choose the negative solution as corresponding to the physical one. Sorry, there should be an extra time here variable here. So you can see once you substitute 0 down over here, you're actually going to get 0 for my angle. All right, what I would kind of do, what's often done here is let's just write this in a little bit of a nicer way. Let's maybe factor out an L over A term, and you're left with this. 1 minus square root of 1 minus 2 omega 0. This term here becomes A over L and multiplied by time. So that is the analytical solution for the 2D tetherball, right? Describing you the exact angle as a function of time for it wrapping around that post, which has a radius equal to A. So let's go make a plot of this and see what the solutions look like. All right, so this is how I set up my problem over here. I started with a length here, where is going to be equal to basically 2 circumferences. So it's going to be 2 times 2 pi times A. That was kind of my length of the string that I considered over here. All right, now if I do that, let's go ahead and look at what the angle is. All right, so what you have to do now is substitute that length into this expression. You could substitute that into over here. So what I'm going to end up doing is basically doing 2 turns around. Okay, the amount of time it takes for that mass to hit all the way in this position over here is going to be when this term here goes to 0. When I set that equals to 0 and I solve it, that'll give me how much time does it take for that mass to swing around 2 complete turns and strike the top of that post. So this is what I'm going to get. I have to solve this. 1 minus 2 omega 0 AL and t equals to 0. All right, so all you have to do now is just solve this for time. So bring that onto the other side. So we're going to get a time which equals to what? This is L over A. And then here I'm going to have a 2 omega 0 down over here at the bottom. And now if I substitute my length here was 4 pi times A. And here I have 2A and omega 0. So let's go cancel out some things. The 4 here, I'm left with this. The A's cancel out. And I also chose an initial angular velocity here, which was equal to pi. This was kind of my choice. I just gave it some value here. And if I choose that equals to pi, what you're going to get is that it takes 2 seconds for this mass to wrap around and eventually hit this position. Let me show you those plots. Okay, so let me show you this. So I've got a couple graphs here. First of all, the length of that string was 4 pi times the radius of the peg, and A was 0.1 meters. That means I've started over here at this initial condition here, which is approximately 4 pi times 0.1, so 1.2 something. All right, and then you can see as it wraps around, look what's happening over here, right? As it wraps around, that length of the string is getting smaller, and it starts spinning faster and faster until it hits, and it makes contact with it right here. On the right-hand side here, I'm just showing you the actual trajectory here, just not as an animation, just showing you again that that mass is going to hit right over here at the top, just because of the length that I picked for that string. Now you can go ahead and plot some of the dynamic variables, for example. What does the angle theta, what does this function here that I derived look like as a function of time? I'm showing you two plots here. I've got the theory, which is this curve up here, and the simulation just outputs a whole bunch of times. I'll share with you that simulation in just a second here. But what happens over here is that it starts off, it's pretty constant, right? That slope is pretty constant, and then it starts spinning faster and faster, and the slope really takes off right here. So you're going to hit that final, right at the end here, you're going really, really fast. If you really want to see what that angular velocity does, you can also plot it by just differentiating this angle theta with respect to time. And so the scale is probably not the best. You don't see this initial value, but remember that at time 0 here, I'm starting at pi radians per second. So it's just a little bit above the 0. And then everything kind of behaves kind of nicely right up until you approach that 2-second limit, and you're hitting very, very large angular velocities for this problem. The other things we could look at are the energy, for example. So I had an expression in my Lagrangian for the kinetic energy. And if I plot that as a function of time during this simulation, or using those variables, you can show that that kinetic energy term is indeed a constant term. That is depicted here by the blue line as a function of time. Here I'm plotting the energy divided by that initial energy that it had. So it's just a normalized value equal to 1 as a function of time. All right, the other quantity that I was interested in was that angular momentum. And here is the plot of the angular momentum as a function of time. It's that green line over here. Notice that the angular momentum is not constant for this problem. That is because, as we showed, that the tension does produce a torque, and it does reduce the angular momentum as a function of time. But anyway, if you just plot this value here as a function of time, you can show what this curve looks like. All right, so they're all the dynamical properties that I looked at for this problem. All right, for the last part, I thought I'd share with you just a little bit of Python code. Again, the whole goal was to solve this. It's really a nonlinear differential equation here, second order equation. For that, what I did was I have a little bit of Python code here that defines the function here. I have an effective length, and that length is just that denominator term, which is the length of the string minus the radius of my cylinder, which I called rpeg over here, and then multiplied by that angle, which I call theta 2. Okay, now in order to solve this, this is the equation here that I've defined for that second derivative with respect to time. And here it is. It has rpeg, omega squared, and divided by that effective length. All right, what I'm going to do here is I'm going to copy this Python code that I have that creates this animation and also makes all the plots that I've showed you before. I'm going to put a link of that Python code in the description. If you want to play around with it, feel free to do so. Again, I'm a physicist, I'm not a computer scientist, so beware, but I think I've annotated enough that you should be able to understand the code and hopefully make some changes as you feel you want to study those different cases. All right, folks, that is it for me. Thank you very much for watching. Hopefully you appreciate this video and you've learned something, and we'll see you next time.